in orbit. Planets move in ellipses around the sun. One major problem that remained after they decided or discovered this was that no one really understood why they orbited this way. 80 years after Kepler decided that planets moved around the sun, Isaac Newton stated the law of universal gravitation. There is a gravitational force between all objects that pulls them together. When no force acts on an object, it will move in a straight line at a constant speed. The planets are always moving, and the force of gravity pulls them towards the sun, which balances their tendency to move in a straight line. So we know that objects fall towards Earth. So Earth is pulling those objects towards it. That is gravity. If there is no gravity, no force acts on it, it'll move in a straight line at a constant speed. So if we didn't have gravity and we pushed a can of pop away from us, that can would continue to move at that constant speed that it left our hands until it hit something. So the planets, again, were always moving, and the force of gravity pulls them towards whatever they're moving around, which in this case is the sun, and that's what puts them into orbit. We see this in a diagram here. Gravity connects these two objects. The natural tendency of the Earth, because it's moving, it has forward motion, would be to continue in that direction. If, like, this was a rope and it broke, the planet would continue onwards this way. However, gravity is constant. We see that. So these two forces add together and keep it in a circular orbit. Circular, again, being elliptical in our case. So again, gravity is the driving force between all planetary, which we can also refer to as satellite motion. As a planet is closer to the sun, the force of gravity it feels will be greater, and the planet moves faster. That's why the orbits of inner planets are quite short. The further away, the less gravity that planet feels, and the longer it takes to orbit the sun. Gravitational assist is used to launch rockets and satellites into orbit, or by space things coming into Earth's orbit. What we see is that if we have something come around Earth or a planet with lots of momentum, gravity starts to attract it to that planet. However, it still had that forward momentum, and therefore it gets shifted into orbit. So this planet has constant motion, and this planet also has an attraction to whatever this is. Therefore, it will continue to make a circular orbit. Rockets were originally used as fireworks and weapons. There's three basic parts to a rocket. The structural and mechanical elements, like the rocket itself, the engines, the tanks, the stuff on the outside that helps to guide the rocket. We also have fuel, which is a combustible material, and a payload, so whatever the rocket is actually carrying. So if it was for a space flight, the crew cabins, the food, the water, the people, or whatever like satellites or space things that it was carrying up to orbit. Rocket fuel. So rockets need combustible fuel to make them fly. All fuels create exhaust, which comes out the end of the rocket. This exhaust pushes the rocket forward, because for every action, there is an equal and opposite reaction. So if we have our rocket, again, the fire and the exhaust is pushing downwards, and so that's what allows the rocket to move upwards, that equal and opposite reaction. The speed of the exhaust leaving the rocket is called the exhaust velocity, and this determines the range of the rocket, or how high a rocket will travel. The higher the exhaust velocity, the higher the rocket will go. Solid fuels have a lower exhaust velocity than liquid fuels. Solid fuels is where rocketry started. And of course, we've moved into liquid fuels like hydrogen. The gravitational escape velocity, so to escape Earth's gravity, we need to be going 28,000 kilometers an hour to escape the gravitational pull of the Earth. A multi-stage rocket was designed in 1926, and it was also a liquid fuel. A multi-stage rocket has more than one section that drops off once its fuel is used up, making the rest of the rocket lighter and able to fly higher and faster. So fuel stored in the bottom of a rocket. Once this is burned up, this piece falls off and the next fuel would have lit and continues, and again falls off continuously until it's out of orbit. The V2 rocket was designed by Wernher von Braun, and he built the first ballistic missile for the Germans during World War II. The ballistic missile is a bomb that is powered by rocket engines. This V2 rocket successfully found a target that was 200 kilometers away. The Americans, of course, were intrigued by this, and they captured him and his whole team and sent them to the US to continue developing rockets for the US. This team helped to launch the US space program. However, the Russians were not far behind. We can use rocket engines to get spacecraft out of our atmosphere and into the orbit, but we can't send heavy spacecraft on long journeys through the solar system powered with just rocket engines. So instead, scientists again use a technique called gravitational assist, using the gravity of a large object like a planet to slingshot and accelerate, using the extra speed that it gains to propel it in the direction it needs to go. There's a video here on gravitational assist. So the idea is that we don't just use gravitational assist to keep things in our own orbit, but that we can use it to, for instance, go around the moon, like the first moon journey. One of these was the Apollo 13. Apollo 13 had an explosion on board, and they used the gravitational assist of the moon. So they went around the backside of the moon using that to create momentum to make it back to Earth. Without the gravity assist from the moon, if they had just tried to reverse their motion, coming to a stop in space, of course, where there's no gravity, and then reversing to come back to Earth, they likely would not have made it. If you're at all interested, the BBC podcast 13 Minutes to the Moon Season 2 talks all about the Apollo 13 mission and how incredible it was for space exploration. And really just math and space travel. All right, computers. 1960s, Americans and Russians were racing to launch spacecraft into orbit using rockets. They needed computers to calculate and control these orbits. As computers became smaller, they were then put on board the spacecraft and worked with computers on the ground to calculate orbits, locate satellites and other space junk, collect, store, and analyze data, and to move around those obstacles in orbit. Computers were also used to clarify images, so CCDs, charge-coupled devices, recording images by converting light signals into digital formats, and are processed by removing the noise or what isn't being focused and sharpening the image. Satellite is an object that orbits a planet. So moons are technically natural satellites of planets, and planets are natural satellites of stars, like the sun. Any man-made object orbiting Earth is called an artificial satellite. Applications of satellites could be remote sensing or monitoring, communications or weather, mapping, navigation, and military satellites. As of July 5th, 2016, the U.S. Strategic Command tracked over 17,000 artificial objects in orbit above the Earth, including only 1,400 operational satellites. There are many, many more times, many like small pieces of space junk that are orbiting the Earth, which can cause problems in the future, because if space junk collides with a satellite, it could knock it out of its perfect orbit, damage it, etc. There's a little video here for the history and use of satellites. Geosynchronous satellites always orbit above the same point on Earth, and they move at the same speed and in the same direction as the Earth's rotation. They appear to be motionless over a point on Earth. This is good for radio or TV. For instance, we don't want to watch Russian television stations, for instance, so they keep their TV satellites above their own country, and we keep ours over our own country. Monitoring and forecasting weather. Again, we're more interested with the weather from our own location than a location in Sydney, Australia. And military and government surveillance. We want to surveil a particular area. We are going to keep that satellite over that area. These have a period of orbit of 24 hours. So they orbit the Earth in a 24-hour period of time at an altitude of 3,600 kilometers and a very specific speed to keep it at that 24-hour period. A low orbit satellite have a continuous circular orbit around the Earth. They travel in different paths over the Earth's surface for communication. So better communication because it reduces lag in conversation. Again, geosynchronous is pretty far out in comparison to what we're talking about here. Low Earth orbit are here. These satellites travel faster than the rotation of Earth. Again, these are better for communications because the time it takes for the signal to go to the satellite and come back to wherever it needs to go is shorter. Remote sensing, so making digital images of the Earth's surface and sending it back. We want to see the entire Earth's surface, not just one part. So these can orbit the Earth every 90 to 100 minutes is really the orbit speed is quite high. Remote sensing is taking measurements of Earth from space. These are used for measuring and monitoring the Earth, like vegetation cover of land, so healthy versus unhealthy areas of vegetation, forest health, so we can see what's going on in a forest, water quality and pollution, so we can see algal blooms, oil spills, the floating plastic in our oceans can be viewed from space. They can take the water temperature. We can see erosion of our land, how much of our land is used in cities, and we can map the climate. GPS, or Global Positioning System, is another type of satellite. It allows us to know exactly where we are on Earth at any one time. Of course, we use GPS so much these days. It uses multiple satellites and what's called trilateration, not triangulation, to calculate your distance to each satellite. So it uses at least 3, but 4 is best. So once it decides how far away you are, the distance is drawn as a circle around that satellite. So how far we are away from satellite 2 is transitioned into kind of an orb around satellite 2. It's also done around satellite 1. And so where these intersect is potentially where you could be. 3 is necessary because remember, these are 3-dimensional spheres around a satellite. And so we can find a location where all 3 meet, and that's where you are. There's a great video on how this works. It gets a little bit complex, but the first at least half is really great explanation of GPS. Some practice, make sure you take a look at the learning guide, and there's some extra practice on page 408 of your textbook.